We're pleased to welcome Assistant Professor Andrea Richard from the Department of Physics and Astronomy. And as her title is, Spilling the Beans on a Whole Latte Elements. Please welcome Professor Richard to the lecture. Thank you.
Thank you. Thank you. Thank you. So yeah, hi everyone. I'm so excited to be here tonight. When I was asked to give a science cafe, if you know me, you know that I love a good pun, and so I couldn't resist throwing in a coffee pun in the title. So we're going to spill the beans on a whole latte elements today. And as was already mentioned, please feel free to ask questions throughout. Throughout anything, I'm happy to answer. And so I also wanted to mention and give credit that all these figures that are on this first page were actually made using AI. So these were made using Gemini, which is Google's AI. I'm not advertising, I'm just telling you. And so it was pretty fun to give this prompts of like coffee and like nuclear physics and then coffee and astrophysics and to see what it could come up with. And so I'll show some later that I thought were pretty funny, pretty good actually. And so yeah, let's just jump right in. So my field of research is called nuclear astrophysics. So nuclear astrophysics combines nuclear science with the field of astronomy and astrophysics. And so since everything in this talk basically is going to be coffee themed, because we're in a coffee shop, and as I said, I love a good pun, we're going to say that nuclear astrophysics, because it's fall, is like a pumpkin spice latte. Okay, and so in our pumpkin spice latte, we have, what do we have? We have espresso, we have milk, we have ice. This is an iced version because I needed one extra thing. And also we have the syrup, we have the pumpkin spice syrup, right? So in nuclear astrophysics, much like a pumpkin spice latte, there are 4 different fields that kind of make up nuclear astrophysics to make it really unique in what it is, much like without all the ingredients of our pumpkin spice latte, you can't have the pumpkin spice latte. So the first ingredient that we have is astrophysical observations. So if you've ever gone out and like looked up at the night sky, what do you see there? Stars, thank you, planets. You know, sometimes if it's really dark, you can see the Milky Way. And so this is the idea of astrophysical observations, but they're done in a more like sophisticated manner using telescopes or other types of techniques like that, where we're actually physically observing those astrophysical like environments that we're going to talk about today. So let's say that the astrophysical observations are like we can call it the espresso for this one in our pumpkin spice latte. So then the next thing that we need in our latte, since it's iced, is ice cubes. So let's say that our astrophysical models are the second sort of ingredient, and these are our ice cubes. These astrophysical models are these calculations and theories that are developed by other like scientists in order to actually try to understand what's observed in these astrophysical environments. So you look at a star, you want to try to understand like what's going on in that star. These are those astrophysical models. So these are our ice cubes. So now we're down to the last 2 things, the last 2 ingredients sort of in nuclear astrophysics and in our pumpkin spice latte. So one is nuclear theory. So these are theories and models in nuclear physics that allow us to describe like the phenomenon that actually occur in these astrophysical environments that involve nuclei, which we're going to talk about in a second. So let's say that our nuclear theory is, you know, now that I did this, I actually forgot what I said astrophysical observations were, but it's one of the other ingredients. So let's say it's the milk, for instance. And then the last thing is our nuclear physics experiments. So the actual measurements that we do in the laboratory to try to constrain some of these reactions that are happening in astrophysical environments. And this is where I do my work. And so just to be spicy, we'll say that this is the pumpkin spice flavoring in our latte. And so, like I said, much like a pumpkin spice latte, without those 4 ingredients, it can't be a pumpkin spice latte. And without these 4 different subfields in nuclear astrophysics, we can't actually have the field of nuclear astrophysics as a whole. And so now let's talk about what we're trying to actually answer in nuclear astrophysics. So what we're trying to do is take sort of nuclear physics and then combine that with what we understand about elements that make up everything that we see around us. And so for instance, what we're trying to do is look at the big picture by actually examining really, really tiny things. And so if we look at this leaf, for instance, this is a solid object. You see tons of leaves, especially in Athens, right? In a leaf, we look at a single, like a small part of it, and within that leaf, there are tons of different atoms in there. If we zoom into then one of these atoms, at the middle of that atom is the nucleus, and that's what we study in nuclear physics. And so the nucleus is actually a collection of protons and neutrons, just color-coding them with the blue and the red. And the protons are these charged particles, so they're charged positively, and neutrons are neutral particles, and they sort of like all like just mix together to make nuclei, and that's what we study and what I study in my research. And so when we actually want to talk about all the different nuclei that exist, we can actually start by looking at the periodic table. So hopefully everyone's seen some version of a periodic table. But this is a chemical organization of all the elements that are known to exist. And so this number that you see up here, this like 1 that's here, for barium it's 56, that tells you the number of protons that specific nucleus or element has. And that number of protons is actually characteristic to the individual element that you're actually looking at. And so if I tell you that something has 5 protons, what am I looking at? Boron, thank you. Yeah, and so that's, I don't know who answered it. Somebody can get a t-shirt. But that's sort of like what we're doing. And so this particular periodic table is actually showing all the elements color-coded by the astrophysical environment where they're actually created. So what you can see from this periodic table is that the majority of elements that we actually see that make up quite literally everything around us, they come from stars. So what that means is that you're actually made of star stuff. So if anyone ever tells you that you're not cool, you can just say, not true, I'm actually a star. So that's quite nice. And so what we want to try to understand in nuclear astrophysics is actually where all these elements come from and how they're actually created, how they're synthesized. And so in order to answer this question, a great thing to start asking is actually like, just what is everything made of, right? Like, what are you made of? What am I made of? Not to be philosophical, but like scientifically, if we look at the human body, we know that the human body is composed of elements like oxygen, carbon, magnesium, for instance. So like we know really well what the elemental composition is of the human body, right? We can also look at the elemental composition of the earth. So if you're a geologist, maybe this is something that you're more of an expert in than I am. But for the composition of the earth, we know that the earth is like primarily oxygen, so it's like 47% oxygen. It has silicon, and then it has like smaller amounts of things like copper, nickel, and so forth. And so we have like a really good understanding of the composition of the human body, what elements make up you and me, what elements make up the earth. We also have a really good understanding of what makes up physical objects, like your phone, because somebody had to make that, right? It's not like they were just like, poof, magic, like someone had to actually make this. And so what this means is like in the screen, we know there are elements like indium or like gadolinium. We talk about lithium batteries all the time. So there's lithium in the battery of your phone. And then in the electronics, there are things like copper and even really heavy things like lead, And so we have this like very good understanding of like the composition of physical objects like a cell phone, a laptop, coffee, everything here. But in nuclear astrophysics, what we actually want to try to understand is the origin of elements in astrophysical environments like this one, which is a rendition of a neutron star merger. So a neutron star is this very dense object that's like filled with tons of neutrons, and they're in these sort of like very exotic environments in space, and they sort of like rotate around each other, and at some point their paths just start to match up, and then they just smash into each other, and we call this a neutron star merger. And this is actually thought to synthesize over half of those heavy elements from the periodic table. And so what I want to do in my research is understand the origin of elements in environments like this, and specifically measuring the nuclear reactions that happen in these environments. So this brings me to my first AI picture, which is I tried to ask to get an image of neutron star mergers with coffee, and what it gave me is 2 coffee beans merging. So I don't know, it's not, maybe 2 coffee beans merging is not that exciting, but I bet it would be a very tasty drink. So that would be great. And so Now I want to come back after talking about this, like this is the question we want to answer. What is the origin of elements in the universe? What is everything made of? And so I want to come back to this picture of the periodic table, and I have this animation to show you. And this is to say that the periodic table is actually not really enough in the field of nuclear physics for us to really understand what happens in like astrophysical environments. And so what's happening in this is this animation is taking all these elements from the periodic table and it's just plotting them in a different way. And so it's plotting them with increasing number of protons here, that's that element that identifies them, an increasing number of neutrons going this way. And so all these black boxes that you see here, those are those stable elements, the things that make up you, me, coffee, which we love and is the theme of this presentation. And so it fills these in, and then what's going to happen is that everything else that you see here that's color-coded in like the red or the purple, these are radioactive species of those elements, which we're going to talk about on the next slide, and those are called isotopes. And so this picture is a more complete picture of what we actually need to understand what's happening in astrophysical environments. And so this is called the nuclear landscape, or the chart of the nuclides. I like to call it the nuclear physicist expansion pack, because it's just like adding a little bit extra, well, I guess a lot extra actually, to the periodic table. So again, this is plotting the proton number here, neutron number here, and these black boxes, that's directly from the periodic table. Everything else that you see here is a radioactive version of those stable elements, and we call those isotopes. And so you might see, for instance, like oxygen, which I dare say is pretty important because we need to breathe. And so oxygen, for instance, has a couple of stable elements, and then it has a bunch of isotopes, which means they all have the same number of protons, but a differing number of neutrons. And so this picture that I'm showing you here, like I said, is actually much more realistic in what we actually need to be able to understand what happens in astrophysical environments. And so I wanted to take a quick look a little bit closer at this. So what we're going to do is zoom in to this region from hydrogen up to oxygen. And this is called, like I said, the chart of the nuclides, where when you count the number of protons, that tells you the element. So you count these here, 1, 2, 3, 4, 5, and so on. And when you count the number of neutrons, that tells you the isotope. And so if we wanted to look at carbon, for instance, carbon has 6 protons, and then it also has 6 neutrons for the case of carbon-12. So if we have 6 protons and 6 neutrons, we've made carbon-12. So we've made this nucleus. We call it like C12, carbon-12. And carbon's also quite important for all of us since we are carbon life forms. And so this is a sort of an example of how you can make elements by combining numbers of protons and neutrons. So for instance, you could come up here and like choose your own. And so let's say you wanted to make like nitrogen 14. How many protons do we need? 7? Yeah, exactly. And how many neutrons do we need? 7, exactly. And so that's how you could think about making elements kind of this way, just by combining numbers of protons and neutrons. So now that we've talked about the chart of the nuclides and this sort of expansion pack that we take from the periodic table, jumping to this chart of the nuclides, now we're going to actually start talking about some of the astrophysical processes that happen to actually create these elements. So, oh, too fast. Okay. And so this, again, is another picture of this chart of the nuclides. And what we actually observe, so you remember I said that, I think I said it was the coffee. Someone will have to watch the YouTube later and tell me what I said in the first slide. But what you actually see in astrophysical observations are plots that look like this, where on this axis, you're actually looking at the abundance of an element. It's a little bit blurry, I can see. But, and then along this, you're looking at that proton number. And so for an astrophysical environment like the sun actually has a lot of hydrogen and helium, and then it has much less of everything else. So you can see that as the number of protons, the proton number actually increases, the abundance actually decreases. And so we have a lot of hydrogen and helium. And so these are the types of things that I mentioned that we're trying to understand for astrophysical observations. So for these nuclei that you see here, from hydrogen up to lead, these nuclei are actually mostly made through fusion processes. So fusion is kind of like addition, if you want to simplify it to like math in a very like simplistic view. And so what that means, for example, for these elements that you see here, we're trying to make these black boxes, remember, is that what we could do to actually make like a heavier element is we could smash helium-4, which has 2 protons and 2 neutrons, or a carbon-12 nucleus, which has 6 protons and 6 neutrons. We smash those 2 things together, and then a nuclear reaction occurs in that instance. So now we have sort of like the sum of all of these things, and we actually can create oxygen-16 by doing those fusion, like those addition type reactions. And so we form our new element, oxygen-16. It gives off some energy, and that's what we end up detecting in nuclear physics, which we're going to talk about a little bit later. So this is the idea of fusion, and this is what happens for elements that are lighter than iron. So like our hydrogens, like helium, like lithium, things like that. But my research is actually focused on things that are heavier than iron. And so we have to jump towards like things up here. And in this case, these the way that we actually create those nuclei is not through fusion anymore, but through something that's called neutron capture, which we're going to talk about in a couple of slides. But the processes are actually called the slow neutron capture process, S process, and the rapid neutron capture process, or R process. And so these are these kind of like environments, for instance, where you would have a neutron star merger. That's like the R process. And so the thing to take away from this is that more than 50% of the elements in the periodic table are actually created through these processes, the S process and the R process. So if you want to like make some gold, or like figure out where gold comes from, it comes from the R process and the S process. And so if you wanted to figure out where something lighter than iron comes from, like boron, for instance, as we mentioned before, that would not necessarily be S process or R process because it's lighter than iron. So that's just to show you the 2 kind of regimes. And so now I want to talk about what I mean when I say explosive environments. So explosive environments means something where you're in this very exotic, very like sort of like dense state where there's tons of neutrons sort of floating around. And you could have something like the neutron star merger that we already talked about, where these 2 massive dense objects are sort of like rotating around each other. They eventually crash into each other, and like a bunch of nuclei are made from that. And I actually have a calculation to show you later of this actually happening, so you can sort of visualize what gets made in a neutron star merger. Another sort of explosive environment, which you might have heard of, where this type of thing can happen, is called a supernova. So that's pictured here. It's just an artist's rendition. And this is like kind of sad. It's like when a star is like about to die. It's like, pooh, I'm going to explode, you know? And so then we have something like this, you know, a supernova. Please.
So you mean alchemy still lives? And if I wanted to make gold, I could get rich?
Well, you know, you can make a small amount maybe.
But it might cost me a fortune, right?
That's true. The time it would take to make it would be a lot. Yeah, that's true. Yeah, and please feel free to ask questions as we go. So now that we talked about these explosive environments, I want to come back to this picture of the periodic table that we talked about. And so I said that more than 50% of these elements are made in explosive environments. So if you look at the color coding, that would be the orange, the green, the blue, like the light blue. Sorry. And so you can see that like most of these elements in this periodic table are actually made through these explosive environments, which is why it's so important to actually like measure them and like understand what's happening in these environments, because so many of the things that make up things that we see around us are actually made in these environments. So now maybe the question that you want to ask is, what's the deal with all these processes, right? We talked about the S process, we talked about the R process, and so now I'm going to liken the S process and the R process to some coffee beverages, because, as I said, we're in a science cafe, so it feels appropriate. And so the S process, this slow neutron capture process, it's kind of like a latte. So nothing wrong with a latte. I myself am having one. And so, you know, a latte is made up of espresso and milk, right? Maybe some sugar if you want to get fancy. But the S process is kind of like that. This is another AI image, by the way. This is latte plus nucleus. So it's very fun. You'll have to just give it a try and see. And so what the S process actually looks like is something like this. And you don't have to understand anything like the nitty-gritty details of this picture, but these are those stable things coming from the periodic table. And this kind of arrow motion that's like back and forth, this is what we're interested in, and we call that a reaction network. So what does that actually look like? How does it actually work? So back on our theme of gold, let's say that we start with gold, which actually is gold 197. This is stable gold. It could capture a neutron, which essentially means it's just like, please give me your neutron, like this. So we capture a neutron, and so then, we jump over to gold 198. We're just, like I said, we're doing addition here. We add that one neutron to this. So at this point, when you have gold 198, so it could either capture another neutron, because things can sort of just keep going, or it could beta decay. Beta decay is a process by which nuclei want to go to being stable. They want to jump back to stability. And so again, I'm going to liken this to coffee, as always. So if you imagine in this sort of picture that you have here, the neutron capture is what happens when you drink coffee. So let's say I'm gold. Sounds funny. Let's say that I'm gold, 197, and I want to have a coffee. So I'm going to go over here and capture a neutron. And then I'm oh, now I'm so tired, so I'm going to beta decay back over here to Mercury 198. So then, if I wanted to, I could I'm at Mercury now, I could go over here and oh, I need another coffee, capture another neutron. And then I'm ooh, I'm tired. I'm going to go back over here and I'm going to beta decay. That's kind of the idea if you look at these arrows of it really just bounces around the stable things that are sort of making up everything around us. I don't recommend doing this for yourself because I feel like drinking that many coffees is probably not good for you, but nuclei can do what they want. And so this is the idea of the S process.
Can it go back down?
Can it go, so.
Go from Mercury back to gold?
So there are some processes, yes, there's a microphone, but. Yeah.
Sure. I was wondering if you could go back down, so from Mercury back to gold.
Yeah, that's a great question. So there are ways for it to go back down. So here it captures a neutron and it goes to this one. So it could, for instance, emit a proton. So this would be this is Z and then Z plus one of these. So it could emit a neutron and then do that. The probability for that might be low, but it could definitely still happen. So that's a great question. And so this is kind of the S process in a nutshell. We're really just having a coffee, getting tired, having another coffee, getting tired, Like I said, don't do this in real life, unless it's decaf maybe. I don't know, there's a lot of implications. So this is the S process. So now let's talk about the R process. The R process is actually a whole different ballgame. So I found this picture online, and it was listed as one of the most complicated Starbucks orders that's ever been given. And it's 10 pumps of this, 5 pumps of this, 5 of this, 10 of this, whole milk. And so I replaced the name that was written here. This is not my cup, by the way, probably. But I replaced the name that's written here with the name R process. So the R process is kind of the most complicated drink order you can imagine getting. You're I want, a triple venti something, 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 something with 10 shots of this and, all of this business. And so the the R process is actually an entirely different, very complex thing that we're still trying to understand and disentangle. And it's a very active field of research. And so just to give you a similar picture to what we saw in the S process, those neutron captures still happen, but instead of sort of doing the thing where you're have a coffee, get tired, what you're doing instead is you're I will have many, 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 many coffees, and then eventually I will get very tired, and then I will go back this way. So that's kind of the concept of the R process, is that it's in such an explosive, neutron-dense environment that neutron captures can just sort of take off, and then eventually things just beta decay back. And so this is like I said, the idea of the R process. And so things in the R process are actually quite challenging to measure because they're so exotic and so far away from stability, but I think that's what makes it fun. And so as I promised, I said that I would show you a calculation, and so this is an example of one of our ingredients, astrophysical modeling, sort of coupled with nuclear theory, in order to give us predictions of what elements we might expect to make in a neutron star merger environment. So this is a calculation using a code called Skynet, and this is what it looks like. So we start here with some nuclei. They start to capture neutrons, and then it sort of like speeds up, hence the name like rapid neutron capture. And then all of a sudden it just is like, whew, beta decaying back to stability. And this is how the R process kind of occurs. So I told you, like, you know, the S process, what you would kind of see in a similar picture would be like one capture, one beta decay, one capture, one beta decay. So it really like it's slow, you know? They're very aptly named, which is great. And so then this one, in this case, has this instance where you capture many, many, many neutrons before beta decay takes over, because as always, nuclei want to be in their most stable configuration. Same. And so, you know, people are just like nuclei. And so, just to summarize, the S process, it's like a latte. It's great, it's nice. You know, you capture a neutron, you decay. Then the R process, she's got a lot going on, you know, and so that means that's a very complex puzzle that we have to try to understand. And so, like I said, there are many other processes that happen in astrophysical environments to synthesize elements that I didn't talk about. So if you want to like come up later, you can pick your favorite coffee drink, and as long as I know what that is, I'll try to come up with an analogy for these other processes that occur. So now that we've actually talked about the R process and the S process, what do we actually do? What do we do about this? And so in nuclear physics, what we're trying to do is actually measure reaction rates. So this is like how fast or how slow a reaction actually occurs. And so for neutron capture, we're specifically interested in like the time it takes for like a nucleus to like, remember, like capture its neutron and to become more neutron rich. So this is strontium-93, which captures a neutron to become strontium-94. So this rate that I'm talking about is kind of like that story of like the tortoise and the hare. It's like some rates are going to be slow, some are going to be fast. It just like depends. And that all has to go into those calculations, into that network, because there are thousands of nuclei involved in the R process, for instance. And so we have to figure out the timescales for all of those things. And so, you know, if you want to sort of like put reaction rate in the same context of coffee as well, you can do that. Some people drink their coffee really fast, like open it up, pour it in. Some people like to sip their coffee, you know, and so imagine one nucleus wants to sip its coffee for a long time. Another nucleus is like, woohoo, you know, so it just, you know, it varies nucleus to nucleus. So this is what we want to do. We want to measure these reaction rates that tell us how fast or how slow a reaction is, because that tells us how much of an element actually gets made.
So coffee is either hot or cold. How about temperatures with these reactions?
Oh, that's a good question. I thought about this layer and I was like, is this too complicated? So this is another layer that goes into these, is that there are versions of the R process that are like hot, where you're in like a more hot, like a warmer environment, and you have like more neutrons. There's also like a version of the R process called like the cold R process. And so temperature actually plays a big role. And even between like the S process and the R process, they're in very different temperature regimes than like than their counterpart, for example. So that's a great question. So now that we know what we want to measure, was there another question? Sorry. Okay. Now that we know what we want to measure, where do we actually go to measure them? Well, fortunately, for nuclear physics experiments, there are tons of options. So I'll show you a slide at the end of me going to some of these places just for fun. And so in the United States, there are a bunch of university-based labs where you can do this type of science. And so we have one that's actually like literally just that way down the hill. Since there are windows, I can actually tell the direction for where you should walk. So I know it's that way. And so it's called the Edwards Accelerator Lab, which we'll talk about on the next slide. So you can come get a tour anytime if you want, just let me know. Or our lab director is also here, so you can also ask him. And so then it's sort of like internationally, there's also a lot of places that you can go to do these types of research. So it's a very active field, and there's a lot of opportunities to actually be able to do this kind of science. And so one place that you could do this is at the Edwards lab. So this is just a picture of our accelerator lab that you see here. This is the actual accelerator where we accelerate particles and smash them into other particles, or sort of like targets, rather. And this is a picture of the control room. So that example that I told you about helium-4 hitting on carbon-12, that's something that, for instance, we could do at the Edwards lab. There are also other opportunities to do things at laboratories like at Michigan State University, where there's FRIB, which is the Facility for Rare Isotope Beams. This is recently constructed, and it's the #1 nuclear physics facility for radioactive isotope beams in the world. So I do some research here as well. It's very fun. So you sort of pick the reaction you want to measure for the S process or the R process, or my favorite process, the I process, but I didn't mention that. You pick the reaction you want to measure, you find the place that you can actually go and do that, and then you can sort of propose to do the experiment, and you do it. So if you want to go to South Korea to do a measurement, you could do that. If you want to go to Oslo in Norway, you can do that. So there's lots of fun opportunities. And so how does this actually work? So we take our beam that we have here, and so you can think of creating and accelerating a beam kind of I don't actually want to scoot my feet because I don't want to get shocked, but scooting your feet across the floor and you see static electricity in your hair. We sort of accelerate beams or particles? Beams. We accelerate particles, and we call these beams, and so this is, again, an example of helium-4. We hit those onto targets, so you can kind of think of this pool, you have the cue ball, and you hit it into the other balls, and they kind of scatter. And what we're actually measuring is the scattering of those particles and kind of the energy that comes out from those. So this is just an example of this beam hitting this and creating these products. And then it's time to play detective and actually figure out what you're actually seeing from that reaction and what that means. And so the way that we detect these, we use a lot of radiation sort of detectors. So this is just one example where energy comes in, it interacts with the material, we multiply the electronic signal that comes from that, we send it to the data acquisition system, and hopefully we're happy with what we see. And then we end up sort of getting the information that we need to ultimately tie back to the astrophysical environment that we're interested in. So some of the detector arrays, for instance, that I use in my research are pictured here. So they're actually quite complex. They have very different types of geometries. And so this in itself is also a very fun sort of field. And so now I wanted to give you one kind of real-world example before we get to the wrap-up part. And so this is, where does zirconium come from? And so, for instance, let's say we want to understand where this zirconium-94 comes from. So zirconium is actually an important element. It's, for instance, in cubic zirconia. So if you those jewelry, zirconium, there you go. Or zirconium is also resistant to corrosion, so it's used in a lot of industry applications. So if we want to understand how stable zirconium is made, we kind of have to look at this local reaction network like this, and you can see we have to measure 1, 2, 3, 4 neutron captures, 1, 2, 3, 4, 5, 6 beta decays. So it's a really complex picture. So it might make you make this face. You're oh man, But like I said, this is what makes it fun, is the fact that we have this sort of complex picture that we're trying to disentangle things from. And so specifically, I have done research on this reaction and how it impacts zirconium that's produced in astrophysical environments like this one, which is the burning of a star that has carbon and oxygen in it. And so before I close, I want to jump into talking about something that's related to this, which is the women in nuclear science who actually made the field what it is. And so these 3 women that I'm showing here, the first one is Eleanor Margaret Burbidge. Actually, a lot of people call her the mother of nuclear astrophysics because she was the first author on a paper that actually described how elements are synthesized in stars. This was done in the 1950s, and they wrote out, this is the S process. This is what the S process does. This is the R process. This is what the R process does. Without the leadership of Margaret Burbidge, we wouldn't really be able to fully understand, I think, in the same context what we do now about how nuclei are synthesized in stars. Furthermore, the radiation detection that I talked about, we couldn't do that without Marie Curie, right? She discovered radioactivity. And then finally, the way that we actually interpret this, within like nuclear theory has had contributions from people like Maria Gilbert-Meyer. And so without the women that are in the field of nuclear astrophysics and nuclear science, we couldn't have actually made the advances that we have so far today. I also wanted to highlight just a couple of people that I work with across different spaces. So these are women who are like leaders in nuclear astrophysics at the present time. A couple of experimentalists you see here, a stellar observationalist, someone who actually observes different stellar environments, and finally a nuclear theorist here who does like computational astrophysics. And what I want to say on this slide is that, you know, a lot of times we think about science in the context of only one person being good at science, or only one type of person being good at science. And I think that, you know, in nuclear astrophysics, in particular, that subfield has done a really nice job at actually showing that, like, we need diverse voices to actually be able to make up and understand all of the science and all the questions that we want to try to answer. And so, for instance, you know, there's this like social identity wheel that you see here that, like, you know, much like the R process, people are also complicated, right? We have many different, you know, social identities, whether that's, you know, race, gender expression, you know, socioeconomic status, and so forth. And so we have to work to be able to, like, make those spaces in STEM like inclusive for everybody so that everyone can come and join these spaces and be able to do good science and answer these questions. So I really liked this image that someone drew, this Leah Castor, of like, you know, people saying like, we do love science, you know? And on this slide, I'm incorporating some resources here that I think would be really beneficial to read. One that I particularly enjoyed reading this morning, actually, was this piece in The Conversation, which is entitled, "You Can Count Female Physics Nobel Laureates on One Hand." And so of the last 225 Nobel Prizes, only 5 went to women. And so I think this is a really interesting read. And I do think that things in the field in general are getting better, but we all have to put the work in to make that really happen. So as promised, the last thing I'm going to show is me on adventures. So this is just me going to other places, as promised, doing a bunch of like, you know, physics experiments. So here's me at the Edwards lab when I was a grad student. This is me and all of my colleagues in Triumph, which is a lab in Canada. This was during COVID, so you can see we're all like masked up. And then this is me like wearing a lab coat, looking really cool, just like installing some pieces of equipment. And then here I'm looking particularly happy. I was holding a detector, I remember that, it was for a very long time. But yeah, nuclear astrophysics is very fun. And you know, it's a field that tons of people can get into. And so I welcome you to come and chat with me anytime about it. And so, with that, I hope that you've enjoyed me spilling the beans on a whole latte elements. And don't forget that we're all made of star stuff. So thank you, and I'm happy to take questions.
Thank you, Dr. Richard. Wonderful. Who has a question? I still have plenty of T-shirts. Okay, let's get a few questions. We certainly have time for them.
So if we're made of stardust, I assume our stars, like the sun, are also made of stardust?
Yes, that's true. So there's you know, the way that sort of the timeline of events sort of went is like we would have this like neutron star merger that sort of would like eject a bunch of like nuclei, and those nuclei eventually like coalesce and create or like develop the nursery, as they say, where the sun and all the planets are born. And so, yeah, that's true.
So in our sun, there are all of these heavy elements, and they're just sitting there idle waiting for a nova or something like that to happen?
So the sun is honestly mostly like hydrogen and helium.
That's what we learned.
Yeah, exactly, right? And so, yeah, that's true. Thank you. That's right. I did say that. And so, in principle, the sun will go supernova at some point, but the time scale is very, 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 very long, so nobody needs to worry about that for many, 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 many years. So, yeah.
Okay, Andrea, so following up on David's question. So we have a sun, it's hydrogen and helium, and then one day it goes boom. what happens? How do we get those heavier elements over what time frames is all of this happening? And then how does it get back into another planet and then get back into the next generation of quote unquote people on the next planet?
That's a good question. So the timescales are actually quite long for this. And so for instance, the thought process is that like from that first or from a neutron star merger that eventually like would give birth to like a solar system like ours, that timescale is like giga years or something like that. So it's a very, 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 very long timescale. And so like an R process event might be like 30 million years or something like that. So I don't think we're going to see anything. But, sometimes you can see supernova in the night sky, like stars will go supernova. You can see like a bright flash, and you're like, oh, a new star is there. And then the next time you go out, you're like, huh, it's gone, And so that's something that can happen, yeah. But the timescales are quite long for this.
Thank you. So you're looking for stars, and what is going on inside our planet? Is this the same as in the stars or not?
So in the planet, it's
We have core.
in the core, yeah. It's more stable. It's like mostly just iron, and so like people do want to study like reactions that happen like on iron to try to understand like sort of like geophysics type applications, like geonuclear physics, I guess. But in the context of like astrophysics and origin of the elements, I think it's not so like connected maybe, but people that's a whole sort of other like field that people want to study. So since the core is mostly iron, I guess there's some fusion probably that happened before, but I think right now the Earth is just like stable, so which is probably good for all of us. So.
Hi, awesome talk.
Thank you.
I was wondering, I really liked when you visited a bunch of different laboratories across the country and across the oceans and things like that. In your field of physics, would you say that it's a pretty collaborative field and that people working on different R reactions are willing to share information, or is it very competitive?
So especially for the R process, it's very collaborative because if you think back to I don't want to go back to here. Let's see if I can go back to one of these pictures. If you look back at this simulation that I showed, there are actually thousands of nuclei that are involved in this process. So honestly, we kind of have to collaborate because no one person can measure 1,000 nuclei. Sometimes we can't even measure the one reaction that we're really interested in, right? And so it's a very collaborative environment. I would say that most of nuclear astrophysics is like that because the pumpkin spice latte analogy, we need input from everyone else to sort of understand what we're doing in the context of the bigger picture. So it's very collaborative.
That's very nice to hear.
Good. There's someone behind you that has a question, yeah.
So in this animation specifically, all that group of red and green was kind of moving diagonally, and then it all kind of bounced back towards the stable parts all at once. What caused that?
So this is part of the R process. So I can play this again so you can see it. This is part of the nature of the R process is that it's in this sort of very neutron-rich, neutron-dense environment where you have a couple of what we call seed nuclei, like iron, for instance. It's just there. And then it gets into this neutron-rich bath, for lack of a better word. And then it just sort of is ooh, I'm going to capture all these neutrons. So it kind of the distribution that you saw at the beginning was kind of the seed nuclei that sort of started at the beginning. And the reason for this flash really is related to those reaction rates that I mentioned. And so once you get really far out here from this line of stability where the elements in the periodic table are, the reactions actually happen so fast. I was telling you you do this and then you do this. The reactions there are so fast. They're milliseconds or even faster than that. And so the reason that you see that sort of jump and then all of a sudden it's whoosh, that's because those reaction rates are actually quite fast once it gets that far from stability. And that's kind of why.
Hi, Andrea. What a great talk. So you showed all of the radioactive isotopes, and you showed the facilities where they could be studied, and there's sort of some ominous things that I've heard some people say where all of these thousands of measurements perhaps could not be measured in our lifetimes with all of these facilities. Mm-hmm. So what I'm curious about, in your opinion, is what are some of the earmarking checkpoints for the field of nuclear astrophysics where we would say, okay, we really do now understand the formation of the elements. Now we need to turn to a different task for nuclear astrophysics. Will that happen with just an increased number of reactions studied, or is it some other different thing that's yet to be seen?
That's a good question. And so sort of to guide what we actually measure, we have to rely a lot on calculations like these, because in these types of calculations, we have to assume some rate for the neutron capture, so how this nucleus gets to this one gets to this one. And so when we actually vary those rates, up and down by times this one by 10 and then divide this one by 10, we can sort of get a sense for some sensitivity for what key reactions are important. And so we try to target those key reactions first. Once we measure those, we see what the impact is. And honestly, there have been cases where someone says, this is the thing. It's going to solve all of our problems. You measure that and they're like, oh, no effect, right? But maybe that's also indicative of something, because it means that there's some underlying assumption that was not right, and so, sorry. Oh, I'm getting confused. There's a lot of ambient sound. And so, I lost the track for where my thought was going. But really, it's trying to measure those key reactions and seeing things. And honestly, at this point, we haven't really measured almost any R-process neutron capture rates. Beta decay is different because, you don't need that many nuclei to do beta decay, but you need a lot of nuclei to do capture reactions. So if we can even measure a handful of reactions, put them into calculations like this and try to see, then maybe that gives us some guidance for where we should sort of lead things. But there's still a ton of things to do, so I think, there's a lot of work to do if anyone wants to do work.
Here's another question.
So you said that you've basically not measured anything in comparison to how many things there are. What's the main reason that so little have been measured when there's been so many experiments done?
That's a great question. And so for the S process, I should say that process that's very close to stability, basically everything, not everything, but most things have been measured already at least once because of the fact that they're so close to something stable. So it's if you think about taking gold, which I'm stuck on the gold example. But if you think taking gold, that's a stable thing, we know where it comes from, you can sort of quote unquote easily do a neutron capture reaction on that because you can physically make a target out of gold. But if you want to do a capture reaction on even gold 199, which is 2 away from the stable, how would you make a physical quantity out of that thing? And that's the challenge, is that we have to make these targets to bombard them with neutrons to then measure the capture reaction. But we can't really make a neutron target, and we can't make a target of these radioactive things. So that's really the thing that kind of slows us down. And that's why we come up with what I do in my research is other techniques to be able to measure things that are important for those radioactive reactions without doing it sort of in the direct way, which is very, very, very hard. So that's why.
All right. Let's say thank you once again to Dr. Richard for enlightening us.